Today we want to continue talking about derivatives, graphs, and I want to take a particular look at polynomials. First, we want to review the connection between sign, direction, and concavity. The sign of the first derivative tells us about the direction of the function, and the direction of the first derivative tells us about the concavity of the function. Since the second derivative is just the first derivative of the first derivative, the sign of the second derivative tells us about the direction of the first derivative. And that means that the sign of the second derivative tells us about the concavity of the function. One of the things that we're going to be interested in when we're trying to determine the direction of a function or the concavity of a function, one of the kinds of points we're going to be interested in is where the function is flat. Where the function is flat, that could mean that the function is changing from increasing to decreasing or from decreasing to increasing. So points where the function is flat are called critical points, and they indicate possible locations of local maximums, local maximum, or a local minimum. So f prime is flat. Points where f is flat are locations of possible local maximums or local minimums. So it could be a high point, or it could be a low point. Those points are interesting because they could be local maximum, a local minimum.
Professor Leach.
Yeah.
So let's say when f is flat, does that always indicate that there's let's say an inflection point?
No. These are not inflection points. Inflection points are where a function is changing concavity.
Oh, sorry, I meant vertex.
Vertex is a more specific form of these kinds of points. We'll just say a local max or a local minimum. So this is where the function is flat. So these are called, the points where the function is flat are called critical points. Critical points are points where a function is flat and they're locations of possible local maximum or local minimum. It might be that the function is flat at a point, but it's not a local maximum or a local minimum. So that's why these are points where we have a possible local maximum or a local minimum. Other points that we're going to be interested in are points where f is neither concave up nor concave down. So if the function is neither concave up nor concave down at a point, it's a location of a possible inflection point. So it's a possible inflection point. Inflection points are just points where the function is changing concavity. So it's a possible inflection point. An inflection point means the function is changing concavity. So if a function is changing concavity at a point, then we call that an inflection point. Just because a function is neither concave up nor concave down at a point does not guarantee that you have an inflection point. It could be that the function is concave down before is a point where it's neither concave up nor concave down. And it could be afterwards the function is still concave down. So a lot of times we look at this in the context of polynomials. So we can use our knowledge of polynomials to reinforce our notions of inflection points and critical points and local maximums and local minimums. And we can use our knowledge of critical points and inflection points to reinforce our knowledge about polynomials. So let's remind ourselves of some things about polynomials. Let's talk about polynomials. So a polynomial, let's see. Well, actually, I don't want to use A. So a polynomial is a sum of a bunch of powers of x, a sum of a bunch of non-negative integer powers of x. So a polynomial has the form, say p of x, some constant plus some constant times x plus some constant times x squared plus some constant times x cubed, and so on. The important thing to note about a polynomial is that there is going to be some highest power of x. So it'll stop at c sub n x to the n, where c is a constant. So this is what a polynomial looks like. Sometimes the polynomials will be in terms of x minus some other constant, but we're going to start with polynomials centered at 0. So we have a constant times some power of x. The highest power of x that we see, ci is constant for all I, and n is a non-negative integer. Some parts that we want to identify about polynomials. The largest power of n is called the degree of the polynomial. Or sorry, the largest power of x is the degree. That will be the degree of the polynomial. This is an nth degree polynomial. The coefficient of the highest power term, x power of x term, is called the leading coefficient. So from the highest degree term, we get the degree of the polynomial and the leading coefficient of the polynomial. Another significant term that we sometimes want to point out would be the constant term. So c sub 0 is the constant term. Let's talk about some things that we know about polynomials. All right, let's talk about, sometimes this is referred to as the end behavior of a polynomial, even though the polynomials don't have any ends. We sometimes talk about the end behavior of a polynomial. What we're referring to is what happens when x goes to infinity and what happens when x goes to negative infinity. When x is going to infinity, the polynomial will go to infinity or negative infinity. So let's talk about end behavior. And I'll put end in quotes. As x goes to positive or negative infinity, p of x will go to positive or negative infinity. If the leading coefficient is positive, then the polynomial will go to infinity. If the leading coefficient is positive, then p of x will go to positive infinity as x goes to positive infinity. And if the leading coefficient is negative, then p of x goes to negative infinity as x goes to positive infinity. So the leading coefficient tells us what's happening to the right. The leading coefficient tells us what's going on the right side. The leading coefficient tells us what's happening to the right. To figure out what's going on to the left, we first have to look at the leading coefficient to figure out what's going on to the right, and then we'll look at the parity of the degree. That is, whether it's even or odd. And so if the degree is even, then the ends go in the same direction.
Professor,
Yeah,
do you think you could go back to the last page so I can screenshot the last part?
this part.
Yeah, I got it. Thank you.
So the leading coefficient is telling us what's happening on the right. To figure out what's happening on the left, we have to look at the degree, whether it's even or odd. If the degree is even, then we'll say the ends, they're not really ends, but the ends go in the same direction. And if the degree is odd, then the ends go in opposite directions. So the degree tells you if the ends are doing the same thing or opposite things. In between, the polynomial will make a number of turns, changes in direction. In between the ends, the graph will make a number of turns. Turns, by turns, I just mean changes in direction. So this gives us 4 possibilities for what the ends are doing. We could look at the leading coefficient. Can be positive, or the leading coefficient can be negative. The degree can either be even, or the degree can be odd. Two choices for each thing. Means 4 total possibilities. So if the leading coefficient is positive, that means the graph will go to infinity as x goes to infinity. Whether the degree is even or odd, if the leading coefficient is positive, the graph, sometimes we say this, the graph rises to the right. If the leading coefficient is negative, then the graph falls to the right. In between the two ends, so the leading coefficient tells us what's happening on the right. In between the two ends, the graph will make a number of turns. Now, the degree being even or odd tell us whether the ends match or mismatch. If the leading coefficient is positive, then the right side goes up. And if the degree is even, then the left side copies the right side. So the left side is also going up to infinity. If the leading coefficient is positive and the degree is odd, then the ends go in opposite directions. If the leading coefficient is negative, then we know that the graph will fall to the right. If the degree is even, the left side does the same thing as the right side. Goes down towards negative infinity. If the leading coefficient is negative, then the graph falls to the right. If the degree is odd, then the left side does the opposite of the right side. So the leading coefficient tells us that the graph goes up to the right. If the leading coefficient is negative, then the graph goes down to the right. The degree tells us if the ends are going in the same direction. And if the degree is odd, the ends go in opposite directions. This is all information that we can get just looking at the leading coefficient. take a look at an example, just what we can read based on. Suppose that f of x is x cubed minus 9x squared minus 48x plus 52. So we see that the degree is odd and the leading coefficient is positive. Since x cubed is all by itself, that means it's 1x cubed. So the leading coefficient is positive and the degree is odd. So the leading coefficient is positive and the degree is odd. So this tells us that the graph will rise to the right and fall to the left. The leading coefficient is positive, so the graph will go up as x goes to infinity. And since the degree is odd, the other side will go, the left side will do the opposite. So the graph, as x goes to infinity, will go to infinity. That is told to us by the leading coefficient is positive. In between, there will be some turns. And the other side will fall, go towards negative infinity. And that's because the degree is odd. This is just talking about the end behavior of the polynomial based on the leading term. When we think about this end behavior, we're thinking about large values of x, and this is why we only need to worry about the leading term. For large values of x, the only thing that matters in this polynomial is the x cubed. Everything else is too small to be of concern. When x is 1,000,000, this 52 doesn't really matter that much. When x is 1,000,000, even though this term is negative 48 million, that's negative 48 times 10 to the 6, this x to the third is 1,000,000 to the third. That's a 10 to the 18th. 10 to the 18th makes 10 to the 6 irrelevant. If you have 10 to the 18th dollars, you don't even notice if you spent $48 million. $48 million doesn't matter to you because you have 10 to the 18th dollars. Now, if you do have 10 to the 18th dollars, and you are saying, well, I don't want to spend $48 million, then we need to take your money away because you don't understand numbers well enough to have that much money. So for large values of x, x to the third is the only thing that matters. For small values of x, these are more important. If x is only 10, this is 1,000, and this is minus 900. So these two terms, they both matter. And if x is only 10, this is 1,000. 52 matters versus 1,000. But 52 does not matter when compared to, say, 10 to the 18th. Any questions?
Yes, Professor Leach. On the example, so we have x to the third power, then it's the positive, so the co-leading efficient is positive, so on the right go up.
Yes.
And 3 is the odd, so it going down.
Left side goes down.
Yes, left going down. I'm sorry. And then if the power is even, then on the left it will go up correctly.
Correct. It'll do the same thing as the right.
Yes. Here my question: in the turn, is it the critical point or inflection point in this case?
The turns are where we're going to find our critical points.
Or is it critical point?
Yeah, because the turns are going to be the points where the graph changes direction.
Okay. And earlier you said if, just in case, if f is flat, they might not have the critical point, isn't it? Like
No, if f is flat, that's a critical point, but it might not be a turn. The graph can go flat, but then continue to increase afterwards.
okay.
So-
flat. In this case, it's the critical point. Thanks. Good.
Yeah, critical point just means the graph has gone flat, but that's an indication that there's a possible turn, but not necessarily. Let's talk about the number of turns. The number of turns that a polynomial graph will make is 1 less than the degree or less than that by an even number. It's one of those things where you describe it in words and it comes out kind of badly, but it makes sense.
Actually, just one quick question, please. Write the turn here. Could it be critical point? Could it be minimum max or minimum maximum? Could it be right at the turn on this example?
In this
Could it-
example, we could have a maximum and then a minimum. That's one of the possibilities.
Oh, okay. I see.
We've done this one before, so we actually know that this one has a maximum and then a minimum, and then we're
I
done.
see. No, thanks, Professor Leach.
So let's talk about the turns. Because in between this end behavior, we'll have a number of turns. The number of turns is 1 less than the degree, 1 less than the degree. Actually, let's say is. I'm going to go back to my original formulation. The number of turns is an odd number less than the degree. The number of turns will be an odd number less than the degree. What that means, so that means that the maximum number of turns is 1 less than the degree. So the max number of turns is 1 less than the degree, but the number of turns will always be an odd number less than the degree. So if we have a 3rd degree polynomial, since the degree is 3, the maximum number of turns is 1 less than this, 2. Or we can have, it just has to be an odd number less than the degree. So the number of turns is either 2 or 0. So a 3rd degree polynomial will either make 2 turns or 0 turns. So although we know what this one does, either to have this end behavior and either 2 or 0 turns, what that means is this graph either makes 2 turns or 0 turns. That looks like 0 tums.
Professor Rich, what is mean by zero turn? Could you?
Means the graph never changes direction. It's just always increasing.
Oh, okay. Thanks. I see. Thanks.
So the reason that the number of turns has to be even for an odd degree polynomial is that the ends have to go in the same direction. Sorry, the ends have to go in opposite directions. I couldn't have a graph make one turn and have the ends go in opposite directions. If we made a graph with one turn, then the ends have to go in the same direction. To get the ends going in opposite direction, we have to make an even number of turns. Let's look at another example and read the number of turns. Let's say example. G of x is, say, 5x to the 4th minus 35x squared. See what we know about this graph just by looking at its form. The leading coefficient is positive. So the graph goes up to the right. The degree is even. So the left side is the same thing as the right side. The degree is equal to 4. So we either have 3 turns or 1 turn. We got to have at least 1 turn because the ends have to go in the same direction. So either the graph makes 3 turns, 1, 2, 3, or the graph just makes 1 turn, 1. If I tried to make an even number of turns, then the ends would go in opposite directions. So as we're working through, if we just know this about the polynomial, when we start looking for the local maximums and local minimums, we know we're either looking for 3 local maximums, 3 critical points, or just 1 critical point.
Quick question for Professor Rich. So on the turn, on this example, the degree is 4, 3 turn and 1 turn. So every time there's number of turn, then there are a number of critical point or the max or the min.
Yeah, the number of turns will be the number of critical points.
Got it. All right. Thanks. That's very, very good lecture. Thanks.
So let's combine this with some more stuff that we know about polynomials. So let's think about some quadratic stuff. Say q of x is ax squared plus bx plus c. Or in vertex form, a times x minus h squared plus k. We know that a quadratic function will have two complex zeros. This could be either two real zeros, one real zero that counts twice, or two complex zeros. Those are the only things that can happen. I either have a polynomial with two real zeros, or I have a polynomial with one real zero with multiplicity 2, or two complex zeros. The two complex zeros will be complex conjugates. A plus or minus bi. And two complex zeros means we have zero real zeros. So this tells us some stuff about polynomials, specifically polynomials with real coefficients. Actually, don't need to do that yet. So if we think about our third degree polynomial, let's just bring it up again. So we know that f of x, our previous f of x, was x cubed minus 9x squared minus 48x plus 52. We know that since this is third degree, this makes two terms or one term. Oh, sorry, two terms or zero terms. So the degree is 3. So there are the number of terms is 2 or 0. This makes sense with what we know about quadratic stuff. F of x is a cubic polynomial, so f prime of x will be a quadratic polynomial. And since f prime is a quadratic, f prime will have either two real zeros or no real zeros. There's another possibility if we have one real zero. We'll have to think about that, how many turns that's going to make. We know it can't be one turn. So for a cubic polynomial, since the derivative is going to be quadratic, we know we'll have two real zeros because the quadratic equation will have will have two solutions, or it could have no solutions, or it could have one solution that gets counted twice, where the vertex is just sitting on the x-axis. Think about how many turns that's going to lead to. And what's going on with the graph if we see that? Any questions?
Yes, Professor Rich. On the f prime, the 3x to the second power, could
Yeah.
you please show us 0 real, 0 for 0 turn? How
No, we just know that it's one of these three. This
Yeah.
particular f prime has two real zeros because we did this problem before. But if we start off with a cubic, the derivative is quadratic, and so we'll have two real zeros, 0 real zeros, or 1 real zero counted twice. In this case, for this particular f, it's this one right here, because we know what this graph looks like. We know that this graph makes two turns.
Okay.
All right. This is what I want you to think about. I want you to start thinking about what you know about polynomials, because there's always more to know about polynomials. We become spoiled with all the easy access to graphing and things like that. So we forget about things like Descartes' rule of signs and the rational zero theorem, like really cool stuff about polynomials. All right, we'll talk more about this, this polynomial business tomorrow. And we'll talk about why we only have to stop at, for polynomials with real coefficients, we can stop at quadratic. We only have to go that far. All right, that's going to do it for today. I'll see y'all on tomorrow. Everybody have a good day, and thanks for playing.